Some of you, dear contestants, are very young, so perhaps you do not know who is Professor Terence Tao. So just a few words of introduction. He participated at the IMO when he was, for the first time, when he was 11 years old, and he received a bronze medal. Next year, he came back and he received a silver medal. After that, at the age of 13, he received a gold medal, and he was the youngest participant to receive a gold medal. Then he, got bored and he went to university, and he didn't participate at the IMO anymore. Now he is a professor at the University of California, LA, and I can say that he is definitely the biggest IMO star, and of course one of the most influential mathematicians of our time. Especially for you, Professor Terence Tao.
Thank you. I'm very happy to be back here at an IMO. The time I had at the IMO was one of the most fun times of my life. I still look back on it fondly. I hope you all had fun, not just in the competition, whether you get a good score or not, but also in the social activities. It's really, they always host a really good event here. So my talk is on AI and more generally machine assistance in mathematics. So you've all heard about AI and how it's changing everything. I think earlier today there was a talk by DeepMind on how they released a new product, Alpha Geometry, that can answer some IMO geometry questions now. And there will be a presentation on the AI Math Olympiad right after my talk, actually, so please stay after my talk for that. So I'll be talking more about how these tools are beginning to change research mathematics, which is different from competition mathematics. Instead of having 3 hours or whatever to solve a problem, you take months, and sometimes you don't solve the problem, then you have to change the problem. It is definitely not the same as math competitions, although there's some overlap in skills. So it's all very exciting, and it's beginning to be transformative. But on the other hand, there's also a sense of continuity. We've actually been using computers and machines to do mathematics for a long time, and it's just the nature, the way in which we're doing it is changing. But it actually is following on a long tradition of machine assistance. So here's a question. How long have we been using machines to do mathematics? And the answer is thousands of years. I mean, okay, here's a machine that the Romans used to do mathematics. Okay, the abacus, one of the early machines. There's even some earlier ones. Okay, so that's kind of boring. Okay, so that's not a very smart machine. What about computers? All right, how long have we been using computers to do mathematics? That's about 300, 400 years. I think that's a bit weird because our modern computers we didn't have the electronic computers until the 1930s and 1940s. But computers weren't always electronic. Before that, they were mechanical, and then before that, they were human. The computer was actually a job profession, someone who computes. Here is a cluster of computers during the World War. So to compute ballistics and other things, they had a whole cluster of computers who were usually girls because the men were off fighting the war, with lots of adding machines. And it was basically, there were programmers who basically just told the girls what to do. And the basic unit of computational power at the time was not the CPU, it was the kilogirl. It's a kilogram hour, so how much computation you can do with 1,000 girls working like this for 1 hour. But we've been using computers actually even before that, as I said, since the 1700s or even earlier. The most basic use of computers in those times was to build tables. So you may have heard of the logarithm tables of Napier. If you wanted to compute sines and cosines and so forth, right, you used a computer to generate these huge tables. When I was still in high school, we still, in our curriculum, learned how to use these tables. They were just being phased out. Because of course now we have calculators and now computers. We still use tables today. I mean, in mathematical research, we rely on tables. We call them databases now, but they're still the same thing. There are many important results in mathematics that were first discovered through tables. In number theory, one of the most fundamental results in number theory is called the prime number theorem. It tells you roughly how many primes there are up to a large number x. And it was discovered by Legendre and Gauss. They couldn't prove it, but they conjectured it to be true because Gauss and others, they basically had computers. In fact, Gauss himself was a bit of a computer to compute tables of the first million primes and try to find patterns. And then a couple of centuries later, there's another really important conjecture. So the prime number theorem was eventually proven in like 1907 or so. But there's another really central problem in number theory called the Burchard-Swinton-Dye conjecture, which I won't talk about here. But it was also first discovered by looking at lots and lots of tables, this time tables of data about elliptic curves. A table that lots and lots of mathematicians use now, including myself, is something called the Online Encyclopedia of Integer Sequences. Maybe you've encountered it yourself. So you may recognize many integer sequences just from memory. Like if I tell you the sequence 1, 1, 2, 3, 5, 8, 13, you know what that is. That's the Fibonacci sequence. And the OEIS is a database of like hundreds of thousands of sequences like this. Many times when a mathematician is working on a research problem, there is some natural sequence of numbers associated. Maybe there's a sequence of spaces depending on n, and you compute the dimension or how many, or the cardinality of a set or something. You can compute the first 5 or 6 of these or 10 of these numbers, put it, and then compare it into the OEIS. And if you're lucky, this sequence has already been put there by somebody else who has, and it came from it was discovered with from a completely different source, coming from studying some other mathematical problem. And then that really gives you a big clue that there's a connection between two problems. And many, many promising productive research has come up that way. Okay, so tables are one of the earliest ways we've been using computers. Most famous, when you think of using computers to do mathematics, you think of number crunching. The formal name for this is scientific computation. So you want to do a very big calculation, and you just have to do lots and lots of arithmetic. You source it out to a computer. And so we've been doing that since the 1920s. Maybe the first person to really do a scientific computation was Hendrik Lorentz. So he was tasked by, I think, the Dutch to figure out what's going to happen. They wanted to build a really giant dike, the Athus dike. And they wanted to know what happened to the water flow. And so they had to model some fluid equations. And so he used a whole bunch of human computers, actually, to work this out. He had to invent floating point arithmetic to do this. So he realized that if you wanted to get a lot of people to do a lot of calculations very quickly, you should represent lots of numbers of different magnitudes as floating points. So, of course, we now use computers to model all kinds of things. If you're solving lots of linear equations or partial differential equations, you want to count some combinatorial, do some combinatorial calculations. You can also solve algebra problems. So like in principle, like all the geometry questions, well, not quite all, but many of the geometry questions you see at Olympiads can be solved in principle by a scientific computation. There are these algebra packages that can solve, you can turn any geometry problem, say involving 10 points and some lines and circles, into a system of equations with, I don't know, 20 real variables and some 20 unknowns, and just whack it into, Sage or Maple or something. Unfortunately, once it gets beyond a certain size, the complexity becomes exponential, or even double exponential. And so until recently, it was not really feasible to just brute force these problems with just standard computer algebra packages. But now with AI assistance, maybe it's more promising. So you heard her talk about that this morning. Another type of scientific computation that has become quite powerful is what are called SAT solvers, satisfiability solvers. So these are meant to solve kind of, basically they solve logic puzzles. Like, if you have 10 statements or maybe 1,000 statements that are true or false, And you know that maybe if the third statement is true and the sixth statement is true, then the seventh statement must be false. And if you're given a whole bunch of constraints like that, a SAT solver will try to take all this information and conclude, can you prove a certain combination of these sentences or not? And then there's a more fancy version of a SAT solver called a SMT solver, satisfiability modular theories, where you also have some variables, X, Y, and Z, and you assume some laws like maybe there's an addition operation, and addition is commutative and associative. And you plug in these laws as well as some other facts, and you try to just brute force, can you deduce some conclusion out of some finite set of hypotheses? So those are quite powerful, but unfortunately they also scale they don't scale well at all. Again, the time complexity to solve them grows exponentially, and so once you get past 1,000 or so propositions, it becomes really, really hard for these solvers to actually run in any reasonable amount of time. But they can actually solve some problems. So one recent success, for example, here's a problem in combinatorics, which probably will only ever be solved by computer. This will not be possible to solve by a human, I think, unassisted. So it concerned what was called the Pythagorean triple problem, which was unsolved until this big computer SAT solver calculation. So the question is, you take the natural numbers and you color them two colors, red or blue. And the question is it true that no matter how you color these two the natural numbers, one of the colors must contain a Pythagorean triple, ABC, three numbers that which form the sides of a right angle triangle, like 3, 4, 5. And so this was not known to be true. We have no sort of human proof of this, but we have a computer proof. It is now known that, in fact, you don't need all the natural numbers. You just need to go up to 7,824. That no matter how many ways you can color 7,824 into two color classes, one of them will contain a Pythagorean triple. Now there's 2 to the 7,824 such classes. You can't do it by brute force. Okay, so you have to be somewhat clever, but it is possible. And then if you do, okay, and then if 7,825, sorry, once you have 7,825, you must have a Pythagorean triple. There was an example of 7,824 where there's no Pythagorean triple in either class. So that's provable. It actually, I think it's the, at the time it was the world's longest proof ever. I think now it's the second longest proof. The proof required 7 CPU years of computation, and it generated a proof certificate. So the actual proof is 200 terabytes long, although it's since been compressed to a mere 86 gigabytes. So this is one way in which we're using computers just to do basically enormous case analysis. Okay, so that's a sort of fairly obvious way to use computers. But in recent years, we're beginning to use computers in more creative ways. So there are 3 ways in which computers are being used to do mathematics, which I think are really exciting, particularly when they are combined with each other, and with the more classical databases, tables, and symbolic computation, scientific computation. So first of all, we're using machine learning, neural networks, to discover new connections and just, find out ways in which different types of mathematics are correlated in ways that you would not see as a human, or unlikely to see as a human. Most splashily, there's large language models, which are, in some sense, very large versions of machine learning algorithms, which can take natural language, like ChatGPT and Cloud and so forth, and they can sometimes generate possible proofs, approaches to problems. Which sometimes they work, sometimes they don't. You'll see a bit more examples of this actually in the talk after mine. But then there's also another technology which is just becoming usable by the everyday mathematician, which are called formal proof assistants. So these are languages. So computer languages you're used to using to write executable code. Programs that do things. Formal proof assistants are languages that you write to check things, to check whether a certain argument is actually true and actually gives you the conclusion from the data. And these have been fairly annoying to use until very recently, and they're becoming now somewhat easy to use, and they're facilitating a lot of interesting math projects that wouldn't have been possible without these proof assistants. And they will combine very well in the future with the other tools that I described here. So I want to talk about sort of these more modern ways to use machines and computers to do mathematics. So I think I started with proof assistance. Yeah, so the first really computer-assisted proof, maybe in history, was the proof of the four-color theorem. Every planar map can be colored in using only 4 colors. That was proven in 1976. This was before proof assistance. There wasn't really, it wouldn't really be called a computer proof nowadays. It's a proof which, it was a massive computation, like half of which was done by a computer and half of which was done by humans. The way they prove the four-color theorem is that you basically induct on the number of countries, and you show that if you have a massive map, there was some subgraph of countries. There's produced a list of about 1,000, 2,000 special subgraphs. And every big graph of countries had to contain, in some sense, one of these subgraphs. That was one thing they had to check. And then they had to check that every time you had a subgraph, you could replace that subgraph with something simpler. And if you could four-color the simpler thing, you could color the main thing. And you had to check these properties. I think they're called dischargeability and reducibility for each of these 1,000 or so graphs. I think one of these tasks they could do by computer, although this was a 1970s computer. I think they had to enter in each graph by hand into this one program and check it. The other task was actually done by a human computer. One of the daughters of one of the authors actually had to spend hours and hours just manually checking this. I think the reducibility thing. It was very tedious. And the process was not perfect. There were lots of little mistakes, and they had to update the table. So it was not, by modern standards, a computer verifiable proof. That was came much later in the 90s, where there was a simpler proof using a mere 700 or so graphs. But now all the things that need to be checked, it was a very precise, well-defined list of properties, and you could write code in your favorite computer language, C or Python or something, and you can check it in a couple pages, in a couple hundred lines of code, in like a few minutes with a modern computer. And then to actually check that it's completely, to write a proof that goes all the way down to the axioms of mathematics, that was done in 2005 using a proof assistant language called Koch. I think it's now renamed Roch. So that was one of the first proofs. And you see there's a huge gap between sort of when the proof first appeared and then when we actually could completely verify by computer. Another famous example is the Kepler conjecture for sphere packing. This is a really old conjecture of Kepler from the 17th century. It's very easy to state. You take a whole bunch of unit spheres, and you want to cover three-dimensional space as efficiently as possible. So there's sort of an obvious way to try to pack spheres. It's just a triangular packing. Like the way you pack oranges at a grocery store. There's also a dual packing called the cubic packing, which has the same density. So there's a density of about 74%, which is sort of the obvious packing. And the question is that the best possible? And this turns out to be a surprisingly hard problem. In 2 dimensions, the hexagonal packing is not too hard to show. It's the best. Only very recently, in 8 and 24 dimensions, do we know the answer as a great work of Yosovska. Maybe she talked about it yesterday. But 3 3 is the only other case that we know, except for 1, which is trivial. But yeah, it was surprisingly difficult to prove. Again, there was no completely human-readable proof of this conjecture. There is a strategy. So, of course, the problem is that there's infinitely many of these these spheres, and the density is an asymptotic thing. So it's not a priori a finite problem that you can just throw at a computer. But you can try to reduce it to a finite problem. So there's a strategy proposed by Toth in the 50s. So every time you have a packing, it subdivides space into these polyhedra called Voronoi regions. Okay, so the Voronoi polytope of a sphere is just all the points which are closer to the center of that sphere than to all the other spheres. Okay, so you can sort of split up space into all these polytopes, and these polytopes have certain volumes. You can also count their faces and their surface areas and so forth. And so they all have these statistics. And the volumes, like the packing density, is very closely related to sort of the average volume of these regions. So if you can say something about kind of how these volumes of these polytopes behave on average, then you could get at least maybe some upper bound onto how efficient packings can be. And you can try to make relations between these polytopes. Like if one polytope is very big, maybe this forces the nearby ones to be very small. And so maybe you can try to find some inequalities connecting the volume of one Voronoi cell to another. And so Tao proposed maybe you should just collect lots and lots of these inequalities and then do some linear program or something, and hopefully you can just derive the right bound of this magic pi over 3 of root 2, which is the right density, from all these inequalities. So people tried this. There were many attempts. Some even claim success, but none have been accepted as actual proofs. The problem was eventually solved first by Thomas Hales and his co-authors. He did basically the same strategy, but using lots of technical tweaks. He changed the cells from Voronoi cells to slightly more fancy cells. And instead of taking the volume, he invented this thing called the score that you assign to each of these. It's the volume plus or minus lots of little ad hoc adjustments. But again, with the aim of trying to create all these linear inequalities between these different scores, and to eventually get upper bounds of the density and to hopefully hit exactly the optimal density. It's a very flexible method. Actually, it's sort of too flexible because there's too many things you can try. There's so many ways you can set up the score and so forth. So there's a quote here. So Samuel Ferguson was the co-author. Sorry, I forgot the name. So Hales and Ferguson realized that every time he encountered problems in trying to minimize his functionals and so forth, he could just change the score and try it again. But then all the things that they checked already, they had to redo. And so the scoring function became more and more complicated. They worked on this for almost a decade, I think. And it became more and more complicated. But with each change, we cut months or years from our work. This incessant fiddling was unpopular with our colleagues. Every time I presented my work in progress at a conference, I was minimizing a different function. Even worse, the function was mildly incompatible with what I did in earlier papers, and this required going back and patching the earlier papers. But they eventually did it. So in 1998, they announced that they had finally found a score which obeyed a whole bunch of linear inequalities and in 150 variables, which they minimized and got their thing. Initially, they did not plan to make this a computer-assisted proof, but as the project became more and more complicated, it was inevitable. They had to use more and more computers. The proof was enormous by the standards of 1998. It was 250 pages of notes and 3 gigabytes of computer programs and data. It actually had a very tough time getting refereed. It got sent to the top journal of mathematics, one of the top, the Annals of Mathematics. And it took 4 years to referee with a panel of 12 referees. And at the end, they said they were 99% certain of the correctness of the proof, but they could not certify the correctness of the computer calculations. And they did a very unusual thing, actually, is that they published the paper with a little caveat from the editors saying this. They have since removed that caveat, actually. At the time, there was a lot more controversy as to whether a computer-assisted proof qualified as an actual proof. Now, I think we are much more comfortable with it. But even after it was published, there was doubt about whether it was really a proof. So this was maybe the first major high-profile problem where there was really a big incentive to really formalize this in a completely, all the way down to first principles in a formal proof language. And so Hales, in fact, created a language, a modification of existing languages to do this. He called it the FlySpec project. He estimated it would take 20 years to formalize his proof. But actually, with the help of 21 collaborators, he actually finally accomplished it in a mere 12 years. It finally appeared in 2014. So we now have sort of complete confidence in this particular result. But it was quite a painful thing to do. So moving now to in the last few years, we've now figured out sort of a better workflow for how to formalize. It's still tedious, but it is getting better. So Peter Schulze, who is a very prominent young mathematician, Fields Medalist, for instance. So he's famous for many things, but he created this amazingly promising area of mathematics it's called condensed mathematics. It deploys the power of algebra, category theory, and all the tools from algebra to apply to functional analysis, the theory of function spaces like Banach spaces and so forth, which an analysis has really been resistant to the method of algebra. But this area of mathematics, in principle, could allow one to solve questions in at least functional analysis, certain types of questions, with algebraic methods. So he set up this whole category of these things called condensed Abelian groups and condensed vector spaces. It would take too long to explain what condensed means. He basically, his thesis is that all our categories of function spaces that we learn in our graduate classes are incorrect, or they're not the natural ones. They're ones with better properties. So he set up this theory, but there was this one very important vanishing theorem which he needed to prove. Okay, so I've stated it here, but I'm not going to explain what any of these words mean, or the symbols mean. But there was a very technical vanishing of a certain category theoretic group that he needed to compute. And without this, the whole theory doesn't have any interesting consequences. So this was sort of a foundation of his theory. So he wrote a blog post about this result. He said he spent a whole year getting obsessed with the proof of this theorem, going almost crazy over it. In the end, we were able to get an argument put down on paper, but no one has dared to look at the details of this, so I still have lingering doubts. With this theorem, the hope that this condensed formalism can be fruitfully applied to functional analysis stands or falls. This theorem is of the utmost foundational importance, so being 99.9% sure is not enough. He said he was happy to see many study groups on condensed mathematics throughout the world, but they all stopped short of the proof of this theorem. This proof is not much fun, so he says this may be my most important theorem today, it better be sure it's correct. So he was also very incentivized to formalize this theorem. Now in a more modern language, proof assistant language called Lean. So Lean is a language that has been developed quite a lot in recent years. There's a crowdsourced effort to develop this massive math library. So rather than deriving everything from the axioms of mathematics, which becomes very tedious the more advanced you go, and this type of mathematics is very advanced. So there's this central math library in Lean that can sort of, that has already proved lots of intermediate results, like the type of things you would see in, say, an undergraduate math course, like, say, the fundamental calculus or basic theorems of group theory or topology, and so forth. These have already been formalized, and so you have a standing base. You're not starting from the axioms, you're starting from roughly an undergraduate level math education. Still a big gap to where you need to go, but it helps. In order to formalize this, they had to add many extra. So the math library was not complete. It's still not complete. There's lots of areas of mathematics, listed on homological algebra, sheaf theory, topos theory, that needed to be added to this library. But in a mere 18 months, they were able to formalize this theorem. And the proof was basically correct. There were some minor technical issues, but nothing really major was discovered. They found some nice simplifications. There were some technical steps that were just too hard to formalize, and so they were forced to find some shortcuts. But actually, the value of this project was more indirect. Firstly, they greatly added to Lean's math library. Okay, so now this math library can handle lots of abstract algebra to a much greater extent than it could before. But also, there was other supporting software that got set up that future formalization projects have started using, including some that I did. So, for example, one tool that was set up in the course of this project was what's called a blueprint. So, taking a huge, like 50-page proof and trying to directly formalize it is really painful. You have to keep the whole proof in your head. But so what we've realized is the right workflow is that you take a big proof, you apply, you first write what's called a blueprint, which sort of breaks up this proof into like hundreds of tiny little steps. Each step you can formalize separately, and then you just put them all together. So you try to break up a huge argument into lots of little pieces. And so you write that first, and then different people in your team can formalize different parts of different steps of your argument. So they also, as a byproduct of this formalization, they also wrote this very nice blueprint. This is probably if you actually want to read the proof as a human, the blueprint is probably the best place to go to now. another spin-off of this, so there's now also this, this formal proof, which is tens of thousands of lines long, but now there's efforts to try to convert that back to a human-readable proof. So another thing that's been developed is that there are now tools that you can take a proof that's been written in, say, this language Lean. So here's an example where there's a proof written of a topological problem, and they converted it back to human-readable proof. So all this text here is a proof that is computer-generated from a formal proof. So it looks like a human proof. It uses the same sort of math language, but it's much more interactive. You can click on any location. I can't do it because it's a static PDF, but you can click on any location here, and it will tell you wherever you are, what are the hypotheses, what you're trying to prove, what's the variables. If there's a step that is too short, you can expand it, and it will explain where it came from, and you can go all the way down to the axioms if you want. I think this is a great, I think in the future textbooks we've written in this interactive style, you formalize them first, and then you can have much more interactive textbooks than currently. Inspired by this, I myself started a project to formalize. Last year I solved a problem in combinatorics with several other people, including Tim Gowers, who's here in the audience. So it's a problem in combinatorics. It's not super important what the problem is. Okay, there's a subset of an energy 2 group. So think of Z mod 2 to the end, like what's called a Hamming cube. And it obeys a property called small doubling. Then there's a certain limit to how big it can be. Okay, but it doesn't really matter what the statement is. But it's a combinatorial statement. We proved it. The proof is about 33 pages. And we formalized it in a relatively record. Actually, it's probably still the fastest formalized actual research paper in 3 weeks in a group project of about 20 people. Using all this blueprint machinery that had been developed in Schultz's project. So basically, and it makes the task of proving things much more open and collaborative, and you get all these nice visualizations. So as I said, the first thing you do is that you take your big theorem and you break it up into lots and lots of little pieces. So the theorem that we have is we call it PFR. I won't explain why. That corresponds to this little bubble at the bottom of this graph here, and then we introduce all these other statements, which the proof of PFR has to depend on several other previous statements, and then these ones depend on previous statements as well. So there's this dependency graph, and they're different colors depending on whether you formalize them or not. So a green proof is a green bubble is a statement that you've already formally proven in your language. A blue bubble is one that hasn't yet been formalized, but is ready to be formalized. Like all the definitions are in place. Someone needs to actually go ahead and do it. And a white bubble, even the statement hasn't been formalized yet. Someone has to write in the statement. So you get this tree of tasks. And then the beauty of this project is that you can get all these people to collaborate on different pieces of this graph independently. So every little bubble corresponds to some statement, and you don't need to understand the whole proof in order to just work on your little piece. So you can so this was a problem in combinatorics, but the people who contributed, there were people from probability, there were people who were not even mathematicians, they were computer programmers, but they were just very good at sort of doing these little mini puzzle type things. And so everyone just sort of just picked one bubble that they think they could do, and they did it. And yeah, in 3 weeks we did the whole thing. It was a really exciting project. And in mathematics we don't normally collaborate with this many people. We collaborate, maybe 5 people is the most I've normally seen. It's because when you collaborate on a big project, you have to trust that everyone's math is correct. And past a certain size, this is just not feasible. But with a project like this, this Lean compiler just automatically checks. You cannot upload anything that doesn't compile. It will get rejected. So you can collaborate with people that you never met before. I met a lot of people. I actually wrote a lot of the letters of recommendation actually coming out of this project. And this is some of an example. Like this is like one little piece of the proof, and so this is what a proof looks like in Lean. It's not exact. I mean, if you know the language, it's human readable, but it looks a little bit unusual. But it really sort of decouples the task of proving things into many different sort of disjoint skills. You can have some people who see the big picture and sort of organize things into little pieces, and then you have people who don't necessarily know all the mathematics, but can just work on little pieces at a time. So I think this will be a more and more common way of doing mathematics going forward. It still is painful to do. Like the tools are not really, they're getting better and user-friendlier, but you still need to have like some expertise in programming. I would say it takes maybe 10 times longer to formalize a proof than to write it by hand. On the other hand, if you want to change a proof, so for example, there was a number 12 that showed up in this theorem. We later improved this 12 to an 11. We got a slightly stronger theorem. And normally, if you do that, you have to rewrite the whole proof. Or like you could maybe cut and paste 12 to 11, but then you have to check you didn't make any mistakes when you did that. But actually, when we formalized this, then we got the improvement. It only took a few days to change the 12 to 11. We just changed the 12 to 11 somewhere, and then the compiler complained at like 5 different places. Now this very specific parts of the proof were not working, and we could just do some targeted fixes. So in fact, so already for some specific types of doing mathematics, actually already the formal approach is actually faster. So now there are actually quite a few big proof formalization projects going on right now. I mean, the biggest is Kevin Buzzard's project. He's just got a big grant to formalize Fermat's last theorem into Lean. He says it will take 5 years to do the most important parts of this proof. He doesn't claim to do the whole thing in 5 years, but that'd be an interesting project. It's already got started. It's already underway, actually. So that is formal proof assistance. Talk about machine learning.